Thank you for joining this webinar on the new AOCS protein digestibility methods that can be used for product development decisions. This relates to food for human consumption. The webinar is co-sponsored by AOCS and IAFNS, the Institute for the Advancement of Food and Nutrition Sciences. I'm Barbara Lyle, one of the moderators for this webinar. My disclosures for the past 36 months are shown on this slide. Over to you, Fiona.
I am Fiona Liu from AOCS. My disclosures for the past 36 months are shown on this slide. AOCS is an international organization focused on advancing the science and technology of oils, fats, proteins, surfactants, and related materials. AOCS Technical Services offers several products to the industry. The 8th edition of AOCS Methods was published in 2024, which includes over 400 expert-validated methods. Many of the AOCS methods are used in the AOCS Laboratory Proficiency Program. Top-performing analysts from the Proficiency Program may be eligible as AOCS-approved chemists. AOCS also offers certified reference materials that are designed for use in quality control and calibration of GMO detection methods. They can confirm regulatory compliance across 7 crop types. Last but not least, AOCS works with other scientific societies, such as ISO and Codex, to promote scientific advancement.
This is Barbara again, and I'll tell you just a little bit about IAFNS. That's how we pronounce that acronym. It's a nonprofit organization that's focused on advancing food and nutrition sciences. We're guided by our core values, scientific integrity, which is centered on transparency, collaboration, and everything is for public benefit. And we accomplish our work by bringing together members from government, industry, and academia to identify areas of common interest and to develop projects that advance the science in those areas. As an organization, IAFNS funds research and convenes experts to deliver a variety of products to include competitively funded research, workshops, dialogues, and then peer-reviewed publications as examples. Today, we are focused on learning protein quality that will adjust your protein content, calibrations or number when you're formulating foods. So if you take protein quality into consideration when you select the ingredients or you decide on your processing methods, then it's necessary for you to be able to adjust your protein when labeling if you want to make claims, and in some cases for the nutrition facts panels. So you need to follow those rules precisely in order to meet the regulations that are in place at that time for the country that you're going to be selling the food in. So our role today is really to focus on screening tools that help you make the decisions up front. And then when you get to the end, you will have to follow the regulations. Health Canada is here today to provide you an overview of their regulations, but know that they differ in every country, including some differences here in the US. Even in countries for which then an in vitro method of determining digestibility factors is not yet utilized, this still becomes a method in your toolbox that's key for you to cost effectively and ethically. And when I say ethically, I mean to do so without the use of animal testing in order to make ingredient and formulation decisions that support your final product testing, right? So this is not so much about final product testing. Ashley will tell you a little bit about that from Health Canada, but what we're going to really tell you up front is how you can screen multiple ingredients or screen varying processing conditions to make smart decisions before you get to the very end where you have to do your labeling. So overall, these methods are going to help you overcome hurdles that make screening your ingredients and processing feasible. There are going to be 5 talks today. The first 2 are shown in the blue box about why it's time to move beyond animal testing and the results of the interlab study that led to the 2 standardized methods of analysis for protein digestibility that AOCS has now approved. Next, we'll have a talk showing how to apply these methods when you're formulating higher quality protein foods based on ingredient and processing choices. And then AOCS will briefly show you how to access the standardized methodologies before we transition to our last talk by Health Canada to demonstrate how all of this relates to protein labeling in Canada as one example of how digestibility is taken into consideration when labeling foods. It's very important that if you have questions that you post them in the questions section of the webinar, not in the comments section. I will be watching the questions section. We're going to be handling the questions such that Adam's first 2 talks will run, and then we'll handle questions after both of those talks run and then after each speaker. I also might choose to take some of the questions to the panel if it looks like they are things that could relate broadly. So know that we probably will get to your question, our intention is, but it may not be right at the time that you post it. With that, I'm going to turn it over to Adam Franchek for the first 2 talks. Thank you.
Hello, everyone. My name is Adam Franchek, and I'm excited to be talking with you about fast, ethical, and scalable, why it's time to move beyond rats for protein label claims. A big thank you to the Institute for the Advancement of Food and Nutritional Sciences and the American Oil Chemist Society for inviting me to speak today. And everyone joining in, live or on the recording, thank you for being here. Before we begin, I'd like to take a moment to acknowledge the recent passing of Dr. James House. Dr. House was not only a mentor and colleague, but also a driving force in advancing our understanding of protein quality evaluation. His vision and foundational work made much of what I'll be sharing today possible. His influence continues to resonate across the field and in the work of so many of us who've had the privilege of learning from him. It's an honor to carry forward a part of his legacy. I previously worked in Dr. House's lab for nearly 10 years, focusing on protein quality assessment using in vitro methods. My experience includes both academic research and work as a research assistant. The funding support I received for my PhD studies is directly related to the topic of today's presentation. There are 3 core themes to this presentation. I'd like to briefly cover the communication of protein messages with a focus on the protein digestibility corrected amino acid score, PDCAS, as our measure of protein quality, and lastly, the focus on in vitro protein digestibility through the pH drop. Current dietary guidelines in Canada and the US have positioned protein as a segment of our plates or meals. Although some items are pictured, including various plant and animal proteins, do consumers know what a protein food is? How might they find this information? One method of relaying protein content messages to consumers is through the Nutrition Facts panel, which reports crude protein content in grams. Alternatively, claims for protein can be made on fronted packaging, such as excellent source of protein, with the addition of percent daily value given on the Nutrition Facts panel in the US. Some of these claims can be demonstrated on existing products, particularly in the plant-based protein sector, milk, snacks, pasta, bread, and simulated meats. However, these claims require substantiation, such as the protein efficiency ratio, the protein digestibility corrected amino acid score, or PDCAS, and the digestible indispensable amino acid score, or DIAS. Recently, Canada has adopted the PDCAS for substantiating protein content claims, in conjunction with the US previously mandating PDCAS in 1993. Additionally, the DIAS has been positioned as a successor of PDCAS, reflecting the improved scientific accuracy of the quality of a protein. However, because DIAS has not been formally accepted for content claims, and Canada and the US both use PDCAS for substantiating protein content claims, this is the primary focus of this presentation and works I will be focusing on. The evidence required to support protein content claims using PDCAS requires both the assessment of protein quality as derived from nitrogen content of a food or ingredient multiplied by a nitrogen conversion factor, which may be a topic of another discussion, and the parameters of quality, the amino acid composition, and protein digestibility. The quality components measure two distinct parameters: the protein digestibility, the extent to which nitrogen or amino acids are digested, absorbed, and ultimately made available for metabolic demands, in addition to the amino acid score, or how well the amino acid pattern matches human amino acid needs. The protein digestibility component is derived from a rat bioassay, to which true protein digestibility, or TPD, is determined. Additionally, the amino acid score is determined from amino acid analysis. A ratio of the indispensable amino acids in the food or ingredient relative to the reference pattern for children aged 2 to 5 is used to find the most limiting amino acid and is selected as the amino acid score. From this, PD-CAS can be calculated from the product of the true protein digestibility and the amino acid score. However, in line with the content of the presentation and why it's time to move beyond rats for protein label claims, primarily focuses on the protein digestibility component and the necessity of the animal component. This is due to the requirements for the rat bioassays, which make assessment of protein digestibility inaccessible, from ethics approval, the feeding trial, feces collection, and specialized facilities and staff. This has inevitably resulted in no substantial database for protein digestibility values, and the necessity of these values being voluntary. Which brings us to the core of the discussion. Can we measure protein digestibility without an animal bioassay? In vitro digestion provides a reasonable alternative. It may overcome costs, time, and ethical considerations through the simulation of components of digestion. With the exception of recent standardized methods, there was quite a variety in vitro digestion methods throughout literature. In theory, supplanting TBD in the calculation of PD-CAS with the in vitro digestibility, or IVPD, is possible, although selecting the quote-unquote best method considers sacrificing whether the method is fast, cheap, or good. Let's briefly consider the types of in vitro digestion models. These methods are often grouped into two categories: static and dynamic systems. Static systems use fixed conditions, such as constant pH, temperature, and enzyme levels, making them relatively simple to operate. In contrast, dynamic systems aim to replicate physiological complexity by adjusting these conditions over time. From this, we may generalize static systems as simple relative to dynamic systems as complex. Within static systems, such as the pH drop, pH stat, two-step, and infogest systems, there is an increasing level of complexity, largely incorporated by different digestion procedures or steps, in addition to how sample protein digestibility is analyzed, whereas dynamic systems include the TIM-1, with the TIM-1 featured here. Much of the work conducted in Dr. House's lab has used these former static systems, the pH drop and pH stat, both of which have considerable overlap in procedure. A small amount of protein is digested using enzymatic solution starting from a pH of 8, and the change in pH is used to estimate protein digestibility for the pH drop. The pH stat, on the other hand, adds sodium hydroxide to maintain a pH of 8, and the final sum of sodium hydroxide is used to estimate protein digestibility. Furthermore, once we correct for the amino acid score in these measures, in other words, to calculate PD-CAS and in vitro PD-CAS, we find an even stronger agreement. Now, in these two past slides, I featured 4 studies. However, to date, there are 11 studies published evaluating some 90 proteins with similar outcome on pH drop, TPD, and PD-CAS. However, during my master's work, we examined what an overall evaluation of 66 proteins might reveal at that time. What we're observing now is a modest decrease in the correlation between TBD and IVPD. There may be several reasons for this. Earlier studies may not have fully captured the natural variability in protein, which is a common challenge in the field, trying to define a variable through correlation. Especially in this case, protein digestibility across a wide range of food ingredients and products. When we subjectively categorize these proteins, we find that excluding those which are untreated or concentrates and focus on those thermally treated proteins, we find this is where the strongest association between IVPD and TBD lies, while still maintaining a large sample size. Finally, what remains consistent across this overall dataset is that when we correct for the same amino acid score, the pH drop method can reliably estimate PD-Cas for these plant-based proteins. At the same time, however, this wasn't the sole focus of the master's work. The goal was to compare the pH drop method with another system, one that's now similar to the InfoGest model, the two-step digestion model. This alternative approach also shows a strong association with PD-Cas. Work in the house lab by Winbui included a comparison of the pH drop method and the InfoGest model by digesting samples with known literature values for TBD and measuring PD-Cas. Although the dataset was smaller, similar outcomes were observed for plant-based proteins, showing only marginal differences between simpler static methods and more complex static approaches. Another interesting study by Taryn Bailey evaluated raw, microwave, baked, boiled, and fried potatoes using 5 different models to assess protein digestibility, including the standard TPD. The results show that all in vitro systems could not accurately determine the protein digestibility of raw potatoes. However, overall, the pH drop and pH stat methods tended to underestimate protein stability, whereas more advanced systems, including the two-step method and TIM, provided more overestimation. While it's important to acknowledge the value of improved digestibility methods and the need to emulate physiological digestion, we should also consider the purpose or application of these methods, as we recognize that increased complexity, time, and cost do not always yield better estimations of TPD or PD-Cas. Given the significant cost associated with these systems, simpler static systems often prove more cost-effective compared to other static or dynamic methods. This is also reflected in the sample throughput. Using my best estimate, simpler methods like the pH drop and pH stat can handle approximately 80 samples run by a single individual in a week, whereas more advanced systems, such as the two-step digestion model or InfoGest, may process only 20 or 10 samples, and the TIM system as few as 5. Notably, these costs also extend to the equipment and training required to operate these more sophisticated systems. To summarize the overall strengths of the pH drop method, we can confidently say that this is the fastest approach, delivering same-day results for protein digestibility. It's also the least expensive of the in vitro methods, and to highlight this contrast, it is vastly more affordable by orders of magnitude than the standard in vivo approach. The pH drop method also requires minimal equipment, most of which is not very sophisticated and features a short, straightforward procedure. However, we should know that these strengths come with certain limitations. The methods estimate protein digestibility using regression models, which may yield stronger correlations for some proteins than for others. Because the pH drop relies on measuring the release of free carboxylic acids in solution, it is not always applicable to proteins that are already highly hydrolyzed, and therefore cannot be further digested. Protein concentrates have also been identified as a notable exception, warranting further investigation. Additionally, in vitro digestion relies on animal-sourced enzymes, and this method is generally less representative of physiological digestion compared to other in vitro models. This may limit its applicability to estimate digestibility for certain proteins or ingredients, particularly those with high buffering capacity, although the specific extent of this limitation remains unclear. Although not the focus of this presentation, it's important to consider that future evaluations and protein content claims may shift towards dias. I'd like to extend the proverbial olive branch here, as the move to dias will still require a robust data set, one that simpler static systems can help generate. As fecal crude protein digestibility can be used to supplant ileal amino acid digestibility in calculating dias. This means that the in vitro protein digestibility estimate by the pH drop method may be sufficient for these estimates. So why do I claim that it's time to move beyond rats for protein label claims? Well, I hope you would agree that we've established 3 things. In vitro digestion methods can estimate TPD. The pH drop demonstrates good association with TPD and excellent associations with PD-Cas, and that the pH drop is simple, fast, and inexpensive. Further evidence of the method's strengths in moving beyond the rat bioassay would be obtaining accreditation for the in vitro method to achieve official method status. In the next presentation, I will also discuss the interlaboratory study conducted to validate the pH drop and pH stat methods, focusing on their reproducibility and repeatability. I would like to once again acknowledge Dr. House, whose contributions and mentorship continue to inspire and guide this work, and everyone from his lab over the years. I'd also like to extend my thanks to the partners who contributed to the studies presented in this work, and again, thank you to IAFNS and AOCS for inviting me to speak today. Thank you everyone for listening, and that concludes the first part of the presentation I'll be giving today. I'm happy to take any questions now, or please feel free to contact me by email or contact me on LinkedIn if you'd like to discuss or learn more. Thank you. Hello again, everyone. I'm Adam Franchik, and I'm back to present the follow-up talk, From Proof to Protocol, Standardized In Vitro Methods for Protein Disability Evaluation. Let's jump right in with a brief disclosure, for which these works are funded with the support of IAFNS. From my previous presentation, I highlighted that protein quality is assessed in Canada and the US to establish protein content claims, but that in vivo assays contribute to the ethical concerns and high costs associated with its evaluation. This can be especially challenging for plant-based proteins. This highlights a growing need for a validated, standardized approach to assess protein quality. If validated, in vitro methods offer a promising, ethical, and cost-effective alternative for assessing protein disability. From this, these methods may empower informed formulation decisions that promote nutritional quality, sustainability, and global food security. Before we continue, I'd like to highlight and expand on this last point. Let's consider protein adequacy. In light of the growing trends in plant-based protein intake, we've observed that increasing consumption of plant-based proteins, particularly at the highest levels of intake, is associated not only with lower total protein intake, but also with poorer protein quality. However, it is important to note that due to the limited availability of reliable protein quality data, a uniform protein digestibility coefficient of 0.8 was applied to all proteins. This highlights the need for a rapid and direct method of protein quality assessment. From a product development perspective, how might products be formulated to obtain protein content claims or improve their nutritional quality? In the previous protein adequacy assessment, high consumption of cereal products, particularly baked goods, was associated with protein quality of poorer quality. In this study, cereal products incorporating chickpea flours subject to various pretreatments were assessed for IVPD Cas. From this, we could determine that products may meet the requirements for a protein content claim, demonstrating that most chickpea treatments can achieve a good protein content claim in breads and pasta. In contrast, conducting similar assessments in vivo will require at least 320 rats and nearly 450 kilograms of product. Finally, protein quality may play a crucial role in achieving sustainability goals, particularly when selecting specific genotypes for particular growing locations. Saw and colleagues demonstrated that different amino acid scoring patterns can lead to varied interpretations of the protein quality of lentils. They also highlighted the broad range of protein quality observed, which was further informed by assessments using in vitro protein disability and NIR. We can start to visualize the added necessity of IVPD, guiding our need for validation. This was conducted through AOCS, using their official collaborative study procedures and funding from IAFNS. Dr. House led the laboratory team, overseeing sample selection and preparation, distribution, data collection, and protocol development. He and his team also vetted and recruited 9 participating laboratories across Canada and the US, with the final data analysis submitted to AOCS. The methods selected included the pH drop and the pH stat. I previously highlighted, as shown here, the overlap in the assessment in both methods. To add, the pH stat was previously positioned as an improvement to the pH drop, as it can overcome the buffering capacity of proteins during digestion through the addition of sodium hydroxide. However, I spoke mostly to the effect of the pH drop, as that is largely where our data associations were completed. Although the pH stat had previously gone through interlaboratory assessment in the 90s and was recommended for use by the FAO, why it was not developed or adopted more broadly is unknown. Because of the similarities between the two methods, both were selected for validation. The study design included 12 protein samples from both plant and animal origins: milk, egg, soy, rice, wheat, peas, lentils, and pinto beans. It covered protein isolates and concentrates, as well as untreated and treated flours. After sample preparation, each sample was subsampled into 3 blind replicates and sent to the participating laboratories for triplicate analysis. So how did things turn out? All laboratories completed and submitted the data for all 12 samples using the pH drop. However, the AOCS analysis identified outliers, resulting in the exclusion of 1 to 2 laboratories for most proteins in the final analysis. The range of protein digestibility values across the samples was 85 to 105%, reflecting a highly digestible set of proteins. Both the repeatability, or within lab consistency, and the reproducibility across laboratory consistency for the pH drop were excellent, both being below 5%. Similarly, all laboratories completed and submitted data for the pH stat, however, with fewer outliers. The range of protein digestibility values across all samples was 81 to 110%, with overall repeatability and reproducibility also being less than 5%. Although this laboratory study did not include an in vivo component, we did source true protein digestibility values from literature to compare to values expressed by the regressions used in the pH drop and pH stat. Notably, there are overestimations in protein digestibility in both methods, particularly with egg white protein being lower in the pH stat, whereas raw pinto beans were also overestimated in both methods. Although raw pinto beans may not have a true protein digestibility value on which to reflect from in literature, we had used a value from navy bean for comparison, which was sourced from a study in the 1960s. Previously, in Dr. House's lab, when evaluating the digestibility of raw pulses, including pinto bean, the study could not be completed due to the animal welfare, as the animals were underweight and discarding feed. When we compare just 11 proteins, removing pinto bean, both methods using a relative difference plot, we can observe that most proteins are within the relative difference of just 10%. Overall, we observe that the pH drop method in these samples produced slightly better reproducibility and repeatability, although this may be due to the greater elimination of laboratory outliers. We were not able to demonstrate the utility of the pH stat method, as few of the proteins exhibited high buffering capacity. We also know that the regressions used estimated values exceeding 100%. It is possible that these values need to be truncated to 100% relative to the casein standard, as this phenomenon may also occur in vivo. Additionally, the regressions were based on slightly different enzyme compositions from studies in the 90s due to the availability of previous enzymes. The interlaboratory study results met the criteria for an official method and were formally adopted by AOCS in late 2024, signifying the successful validation and official availability of these important methods. We've also submitted the results presented here for publication, and they are currently available online as a preprint. While the methods generally provide good estimates for protein samples, there is still work to be done to identify specific proteins or classes of proteins that may not be a good fit. In the meantime, these methods show excellent applicability as a sample screening tool, particularly in large batches of samples. Either method can also serve as a valuable tool for selecting proteins for further study using in vivo or more sophisticated in vitro methods. Future work should refine the regressions and clarify which proteins are best suited for these methods. Additionally, these efforts may contribute to standardizing an in vitro approach for assessing protein content claims. The validation of these methods would not have been made possible without the exceptional work of Dr. House and his team, as well as the extraordinary efforts of the participating laboratories and technical staff. We also acknowledge the funding support from IAFNS, and the collaboration with AOCS. Thank you again, everyone, for listening. That concludes the final presentation for me today. I'll be happy to take any questions, or please feel free to contact me.
Well, thank you, Adam, for both of those talks. I just want to clarify and make sure everyone knows, because we talked about if there were methods that were validated and standardized, but in fact they are, and Adam mentioned that at the end, so I just want to be really clear that both the pH drop and the pH stat in vitro methods now have recently been approved by AOCS as official standardized methods of analysis by that credible organization. That's something that early on had been pointed out to us as being a hurdle for being able to do a non-animal testing version of digestibility assessments. So they were selected because they are both cost effective and they're also ethical. So that's why we picked those. That's not to say there aren't others in the future that could be developed, but certainly right now in your toolbox as of today, there are these two methods that have been standardized. So with that, I'm going to ask Adam a couple of questions. The first one is based on the empirical equations that you showed to calculate the in vitro protein digestibility with these two methods. Someone noted that the lowest calculated digestibility factor was about 75%. So you could confirm if that's correct. But what about foods that have digestibility values that might be lower than that, A? And B, what foods might not be suited for using these assays? So two questions. A is what happens if a digestibility factor really in truth is below 75%, and can you confirm that number? And second, what foods would not be well suited for these assays? Over to you, Adam.
Okay, you can hear me okay?
Mm-hmm.
Sure. Well, thank you for those questions. So to confirm, yes, the lowest value for the true protein digestibility factor estimate is 75%. So this comes back to that first presentation that there might need to be additional regressions if we want to, say, detect proteins where we think their digestibility would be very low. So these would be, proteins that are, from a processing perspective, due to high heat treatment, so they've been burned, or they're, they take on a lot of Maillard reaction products, because these proteins respond well in the assay. So then their pH changes, or their sodium hydroxide that they take up will be very low, because there's no change in those enzymes working on the protein. And then, so digestibility values that are lower, there are a few notable proteins in literature. So things like sorghum, and there's another one that was going to come to mind, but so there are proteins that do show up lower. So the other thing too is they're also challenged by their amino acid score. So if you're thinking about will the method still detect changes? Yes, but the capture of whether it's going to be a good protein, I still think that it would, at 75%, it's still saying that protein might not make a label claim, because there's like these other challenging factors from the amino acid score. And then foods that might not be suitable, I think I'd mentioned proteins that have been hydrolyzed, right? So if they've already undergone hydrolysis, so either enzymatically or otherwise, they won't respond, right, to additional enzymatic hydrolysis, because there's nothing to hydrolyze, so there's no pH change.
That's interesting. So I'm going to see if I have one more question here before I have a wrap-up one. Okay. So can you clarify the difference between the equations for the true and apparent digestibility for the pH drop method?
Clarify between the two?
Yeah, the equations for the true and apparent digestibility for a pH drop method.
Right. So I think earlier in our work from Dr. House's lab, we had used the apparent, and there wasn't really any reason why it was selected. It was just, the method was developed in 1977, so we were just kind of using that as our reference and seeing if it could even measure differences in digestibility and how that would compare to in vivo. So the those works were just, designed for that purpose. And then for these standardized methods, it makes sense to move to a true protein digestibility regression, right? Because that's what you're using in the calculation of PDCAS generally. And there's this kind of 5 to 10% change between apparent to true protein digestibility because it's accounting for endogenous losses. So to select for those two, I think if they're from that 1977 paper from WHO, then they're apparent, right? But if they're from what we put in the standardized method, right, then those are from the true. And then if you're looking at from this presentation, I had suggested or demonstrated some that we developed in lab. So those are just at this stage from kind of like from a literature research perspective that they might have utility. And they're also estimating true. Does that get to the core of the question? Yeah, okay.
Good. If not, if the person who wrote that question still has questions, they can email you, right? Okay, so here's a question in the form of a suggestion.
Yeah.
And I'm going to read the suggestion and then I'm going to add a comment, and then Adam, you're welcome to comment too. So the suggestion was to apply the protein digestibility testing in the matrix of a powdered infant formula and in a liquid infant formula with an intact protein. And I will just comment that IAFNS did not fund any of the foods to be an infant formula. Our choice was perhaps changing the food supply toward diet. So we were really looking at foods for the general population at the time we funded the study. So that's a good suggestion for going forward. And I will also say that it's particularly timely given the recent, in May, release of the National Academies of Sciences report on protein quality and growth monitoring studies. So this is really about the quality factor requirements for infant formulas. I'm literally reading the title of that. And if anyone is interested in this topic, that's definitely to be read. That was published before these methods completed their interlabs study and before they were published as standardized methods. But again, remember that we did not include any infant formula at the time that the first studies were done. So this looks like a future focus. Adam, did you want to comment any more on that suggestion?
Sure. I mean, yeah, it's a good suggestion. From that same paper from the National Academies, there are some suggestions on, what in vitro should cover. And, some of those aspects can't be applied to the pH stat or pH drop because they say things like peristalsis, right? So you can't emulate peristalsis in a simple static method, right? And, if that's important in infant nutrition, right, in terms of digestibility. But it could still be used as a screening in particular because it can also show kinetics, right? So you can see how the protein digests. If you do you're taking pH over time or sodium hydroxide consumption over time. And then also there might need to be modification, which was another suggestion from the paper, right? That infants will have different enzyme quantities or activities or pH, right? Starting pH, things like this. If you're thinking about something like an infogest or something that would emulate additional steps in digestion, right? So maybe there could be a pH stat or pH drop where there's an initial gastric step, in terms of, like a simple digest, so an additional step to kind of keep the method less sophisticated and more for screening purposes, right? But yeah, those would be some of the directions that this method could go.
So just to clarify, the current as standardized methods for pH drop and stat, they would not apply for any hydrolysates. Is that correct?
We haven't tested them exclusively. I speculate that that's part of the reason why some of the concentrates and isolates from plant proteins don't respond well to the pH drop. We don't actually know how they respond in the pH stat. So that would help confirm that, hypothesis, right? So it's hard to say. I can't say definitively.
Okay,
But
so it does seem like there's some
probably not.
follow-up that would be
Yeah.
needed. Yeah,
Yeah.
okay. All right, last call for any questions. I'm looking, I don't see any more. Okay, all right, with that, we're going to go on to the third talk.
Okay, thank you.
Hello, my name is Elaine Krull, and I appreciate the opportunity from the invitation by IAFNS to discuss applying in vitro protein digestibility measures to formulate higher quality protein ingredients and consumer foods. By way of disclosures, I am the owner of EK Science LLC after retiring from DuPont Nutrition and Health, and I serve as a consultant. I'm currently consulting with Evergreen, a division of AB InBev, and I'm receiving remuneration from IAFNS regarding the work presented here. So from a previous presentation, you've seen that in vitro protein digestibility is a cost-effective, ethical, feasible means to screen ingredients and processing parameters to make decisions that maintain or improve protein quality of food products. In vitro measures of protein digestibility increases the ability of food ingredient manufacturers or food companies to understand the impact of processing on protein digestibility. Current regulations allow historic data to be used for protein ingredient digestibility, which is a measure which is required for protein quality measurements, regardless of its processing or formulation into consumer food products, despite data that shows that processing and formulation do affect protein digestibility. Novel protein sources, unfortunately, cannot rely on historic digestibility data, much of which was obtained decades ago, and on probably ingredients that are no longer made in a similar fashion. In vitro, but not in vivo protein digestibility methods can quite easily be used to screen ingredients and processing parameters to make decisions that maintain or improve protein quality of food products. And understanding the impact of processing and formulating is particularly relevant for protein sources that have lower amino acid scores, for instance, plant and novel protein sources, to preserve or enhance their protein quality. And usually this is achieved by increasing digestibility or minimally not decreasing digestibility. An example to show that if you are able to determine protein digestibility, you are able to make a statement about protein quality, which enables manufacturers to differentiate protein foods and provides consumers with more information to make protein choices. And in this example here, we have two product labels. The one on the right actually has less protein in it, but it has a higher or similar percent daily value based on US labeling examples. Digestibility measures allow manufacturers to measure protein quality. Otherwise, if they can't measure protein quality, they aren't able to label a percent daily value on their nutrition facts labels, which leaves the consumer, provides less information to the consumer. The currently required in vivo measures of protein digestibility impedes companies from making protein content claims on novel food products, and this is particular to North America, Canada, and the US. Protein content claims that are based on historic digestibility data also may be providing inaccurate information to consumers. As I mentioned earlier, these historic digestibility data have been, a lot of them has been developed, decades ago. Companies are impeded by high cost and ethical concerns of current in vivo requirements in USA and Canada to make protein quality determinations on their novel products. Existing food products using ingredients with historic digestibility data may not be providing accurate protein content information to consumers. And a lack of protein digestibility measures reduces the ability, as I've indicated, of manufacturers of novel protein ingredients and protein foods to make these protein content claims. And this reduces the ability for consumers to discern protein foods based on accurate protein quality claims. We know from this slide, taken from a review a number of years ago, that many of the processing techniques used in preparing food ingredients and final food products can increase or decrease protein digestibility, as shown in this slide. And I'm not going to go through it, but we do know that processing impacts protein digestibility and hence protein quality. To date, these types of effects on protein digestibility have not really been investigated to any great extent because it's very difficult to do with in vivo methods. But a practical tool to assess the impact of protein processing or formulation, such as the in vitro method, which has now been standardized and validated, make this readily accessible to people developing new food products. And an example of how this can be done is shown on this slide. In this study, the investigators used both in vivo digestibility determined in rat model, which is the current standard for protein quality measures in North America. And they compared that to the pH stat method, which is shown on the x-axis. And they had 3 different grains which were processed into different products, and they wanted to investigate the effects on protein digestibility. So you can see, and they're each indicated, the 3 grains are indicated by color-coded. So you have the raw pearled sorghum, and you can see that the sorghum tortilla and the nixtamal pearled sorghum actually had a decrease in digestibility after processing. The important thing also to note is that the in vitro method really mirrored the in vivo digestibility method, showing that it can discern between small differences in digestibility that occur during protein processing. Now, here's the PD-CAS calculation, and some of you may or may not be familiar with this. And the point of this slide is not to necessarily go through the whole calculation, but the point is that if you measure digestibility of protein by in vivo, which is shown on the top, versus in vitro protein digestibility methods, you do get some differences perhaps in the digestibility measure. But if it's a high quality protein, you can see indicated by the arrows on the extreme right that the final PD-CAS measure is relatively not affected by small changes in digestibility. And this will be more clearly shown in subsequent slides. And basically, just to reiterate, the PD-CAS is based on the ability of the protein to deliver the essential amino acids, and it is compared to the reference amino acid pattern that is that FAO/WHO holds. And in the case of North America, they use the reference pattern for 2 to 5-year-old people. So on this slide, you can see that the top graphs on the first and second graphs are showing the in vivo protein digestibility compared to the total protein digestibility determined in vivo. So the 2 on the top, the graphs on the upper top left, show the digestibility. And you can see that there's a pretty good correlation between in vivo and in vitro measured protein digestibility. And if you look at the bottom graph or the extreme right, you can see that when you compare PD-CAS calculated by in vivo versus in vitro, that the correlations are much stronger and are quite good, above 9.92. And this suggests, and this is probably due to the fact that the PD-CAS score is less influenced by protein digestibility, but more by the amino acid score. So therefore, small differences in digestibility, as I showed earlier, really don't have a significant impact on the differences in PD-CAS. So the PD-CAS, whether it's done in vivo or in vitro, correlate very nicely, as shown on these slides. Now, I'm going to show you an example of where the pH drop method was used to look at in vitro protein digestibility on extracted and processed canola protein. The investigators were trying different extraction and processing methods and wanted to determine whether or not they were losing any protein quality with the processing methods. And you can see that soy protein is used as a comparator on the extreme left of each of the graphs. Protein digestibility is shown on the left, PD-Cas is shown on the right, based on the protein digestibility measures. And you can see that the different methods of extraction, which are indicated, did result in differences in protein digestibility, which is not surprising, and that translated to differences in PD-Cas. The ultrafiltrated products, that the alkaline treated and alkaline ethanol treated ultrafiltered canola protein, offered the best techno functionality for incorporation of foods. And the investigators felt that the compromise in the slight decrease, but not significant decrease in PD-Cas was important to note. But they felt that this was a very minor change, and the improvement in functionality was worth the small reduction in PD-Cas. But again, this shows that using the in vitro method was able to discern these small differences in protein digestibility, which would be virtually impossible to do in a rapid fashion with using the in vivo method. In this graph, the investigators were looking to increase protein content in lupin meat analog products. And they decided to add spirulina protein, a microalgae, which is allowed. It is a food grade material, and it does have a very good amino acid content. And so they added it to the lupin meat mixture at concentrations from 0 to 50%. The raw mixture is indicated in the blue, and the extrudate that they generated is the digestibility values are indicated by the orange bars. And you can see that the addition of the spirulina protein did cause a decrease, as measured by in vitro protein digestibility. It did result in a decrease in protein digestibility, but interestingly, the extrudates had increased digestibility after extrusion. Other parameters were also tested for optimizing the extrusion, and these are shown up in the upper right-hand corner, the things that were tested. And these had relatively minor effects compared to the actual addition of the spirulina itself. And the investigators settled on 30% spirulina as a potential go-ahead because the protein content of the final product and the amino acid score was increased. The addition of microalgae has also been tested in bread, and the addition of microalgae, as we saw with the lupin meat analog experiment in the previous slide, did increase the protein content, and when it was added at a 12% substitution. And they added it as raw microalgae, and they used 3 different types of microalgae as indicated by the TC, CV, and MG. And in Europe, the increase that they saw of protein content by 30% does allow an increased protein claim in the EU without having to prove protein quality. They just, by adding the protein, it increased the bread content by protein content by 30%. You can see that the control, which is the wheat, which is the bread, the control is the bar on the extreme left. You can see that the addition, as I indicated, of the microalgae did decrease the protein digestibility. And in this case, the group used the InfoGest method to determine protein digestibility. And that is an in vitro method that is being developed and is undergoing standardization and validation in Europe. And they were able to show that the treated forms with ethanol actually had further decrease in protein digestibility. But they also noted that when they used calculated DIAS values, and we haven't really discussed DIAS, but it's another measure of protein that is being recommended but not currently accepted. But if they use published data for wheat and microalgae, they've said that even though there's a decrease in the protein digestibility, the increase in protein quality score, again, because of the amino acid score going up, actually increased from was 57 to 66% compared to 46% for the control wheat. The actual final bread products, as shown here, were actually done by the in vitro InfoGest method, and the authors concluded that the increased protein and amino acid score that was contributed by the microalgae compensated for any reduced digestibility. But the ability to look at this change in digestibility is so much easily done when you have an in vitro protein digestibility method. So in summary, the practicality of applying in vitro measures to assess protein quality in food product development has been shown, by when you want to do extraction or processing of the ingredients from raw product, when you're blending and processing different ingredients, and when you want to test the final food products, where you might want to have a variety of different formulations to test, as shown in the last slide. To date, this type of analysis has not been possible due to complexity, cost, slow turnaround, and ethical issues with in vivo protein digestibility measures. The standardized and validated in vitro digestibility methods that were previously discussed in a previous presentation are now available to optimize food product development and can be used right now. And they are standardized across the board, so all different groups can compare and contrast their results. The goal is to be able to have in vitro methods for protein quality determination accepted for protein content claims in North America. And I want to thank you. And if you have any further questions after this webinar, please feel free to contact me at the email address there. Thank you very much.
Well, thank you, Elaine. And there she is live. So, it's so interesting to me that you highlighted that both ingredient choice and processing methods can affect protein digestibility. And I think it's, we always think of ingredient choice, right? I mean, that's an obvious one. What ingredients do you put in? Are they going to be bioavailable? That's kind of a standard interchange between nutrition and product development. But I think we sometimes underestimate the potential positives of using processing choices to make sure that what we put in still is available for absorption, digestion, absorption, and maybe even look for processing methods that would make it better, right? So it's really interesting with protein because processing can reduce it or can increase it. And if you're not looking at all, then you're not making informed decisions, and you might get to the end, put months into developing a new product, and then you go to do your final labeling and you want to make a claim and you realize you didn't take digestibility into account when you made choices about processing and ingredients, of course. So I just think it's really interesting that that's such a big opportunity that perhaps has not been thought about before.
Right.
I also want to just have you share your insights about what currently would be required. So can you just remind us about what data tables are out there that could be used if you didn't or couldn't do an animal testing, which most industry can't these days, and why there's limitations with those, and how you think the animal model some people might think of it as the gold standard, but can you comment on whether you think a rat fecal bioassay in a model in which rats eat their poop, no matter how hard you try to not get them to do that, how relevant is that? Really, like, should we get rid of this myth that that's the gold standard? So kind of two questions there if you want to take that on.
Okay, so with regards to the first, much of the historic data, and I think when companies are trying to make a claim, they will look at the federal regulations, I think from 1991 or 1993, that has tables of digestibility. There also are tables from as far back as 1955 where Merrill and Watt, I believe, compiled all the human in vivo digestibility data. Basically, it's done like you do it in a rat. You collect human feces. So they made a big table. It must have been a tremendous amount of work. And I think you can use those values as well. I'm not sure. I guess it comes to if somebody investigates what are the accepted historic data. But you can appreciate that if you go to historic data now, it's how it closely related to your current product that's made decades later to that is a question. But it is allowed for making PDCAS calculations if you do not want to run the in vivo assay yourself. With regards to the rat as a model, we agree that you're getting a measure of digestibility in a mammalian system, but that's where, and the correlations are pretty good to the, as you can see that Adam had shown and the examples I showed, it does correlate well with digestibility done in vitro. And that's mainly because, well, when you do the rat assay, yes, they're coprophagic, but these animals are kept in wire bottom cages for doing this for the very reason you've mentioned, so that they don't take in what they just excreted. But nonetheless, their amino acid requirements are different. The way they process their intestinal tract is different. So the pig model, which is being used by the DIAS, is clearly a better representation of human digestive tract, and you're looking at amino acid absorption at the ileum, so one may argue that's more physiologic. But it's interesting when people have compared even DIAS to PDCAS using the rat, that the correlations are very good there. So we're looking at a very crude measure of protein digestibility in the long run, and so how you measure it is going to be reliant on the model, and with the rat, at least you have, and in the pig, your animals are all the same species, strain. They are all kept in very uniform conditions, which is probably not even reflective of the human situation, where we know the human data, if you look at the historic, is much more variable. So from that point of view, the rat has been adequate. People argue that the pig is more, but that's getting further into a much more complex and expensive model. And we can see that with both methods, the in vitro method correlates really well, and is probably the underlying thing is just how available is that protein to enzymes that are in the gut. And that's really what we're measuring. So I think that the in vitro assay certainly is sufficient because of the good correlations we've seen with DIAS and with the pig, with the rat model. You're muted, Barb.
Thank you. So correlation is a good word. It's not comparing to a gold standard necessarily
Right.
with the rat assay, but it is a calibration to see whether it's consistently in the same directions, right? And so with these old tables, if you don't have the data there and you're working with a new ingredient, or you're trying to process an ingredient in a new way to make it work in a lot of these innovative, more plant-based protein products, for example, you really are better off doing some sort of a screening assay and not trying to scratch your head and figure out what old data might be close enough.
Right. And you're also taking a risk yourself, because at the end you're going to have to, sell the product, and there have been even challenges, as I think I've indicated at some meetings in the past, where people have challenged PDCAS labels in recent years. So you want to make sure that when you're going to go into your final product development, that your data is accurate, and so it's best to do it yourself. And in vitro allows you to do that.
Okay. So I have a question here about advice you'd give to perhaps a product or product developer or process person, if they're, at the beginning of their project and they're getting ready to develop the ingredients and the processing methods, and they go, oh, I want to make sure that I maintain or even improve, ideally, the protein digestibility as a part of its protein quality. What limitations would you say they should have in mind when they're deciding whether to use an in vitro screening, and which of the two that we've just talked about, just keeping it to those two for now, how would they kind of make that decision based on the limits and the advantages?
You mean you're talking about the pH stat versus the pH drop, making a choice between the two?
Yeah.
Um, yeah, well, and Adam would be the best person to answer that in terms of, and he may want to address that at the end. But both methods would be totally viable. They've been standardized, so you can rely on the results that have been obtained, particularly as you're doing the development and processing. So I think whatever works best in your lab situation, you might want to, at the beginning with your particular protein ingredient, do both methods because they use the same equipment. It's just how one, you're measuring the pH change, the other one, you're maintaining and adding the sodium hydroxide. So if you have any concerns about your particular protein, and Adam raised some concerns about buffering capacities of proteins and other factors that may cause differences, then it's probably best to maybe test both and see which one. If they give you comparable results, and you just go with the one that you find is easiest to use in your lab.
Yeah. So if you see differences, you better understand why you're seeing a difference and make a
Different,
wise choice, right?
right?
Can you also, I know you mentioned it, the sensitivity of the assays when you get to that final product. So let's say you've done screening, you've made smart choices about the ingredients you used, you tried some different processing parameters, you've now got your final product. Um, can you talk about how sensitive the assay is to the changes in digestibility when you're measuring that final product?
Well, as I indicated, the main thing you're going to be looking at to make a label claim is the PD-CAS. And you could see that even small differences in digestibility really become even smaller when you actually do the PD-CAS, which is the measure that you need to make the protein content claim on your product. So, given the fact that your amino acid score is going to be the main driver of that, and as long as you're not decreasing the digestibility significantly, then it's the sensitivity is it's more, it's not as a big a deal for the differences in digestibility.
Okay. And with that, we have a question about how to find the AOCS methods. So we're going to go to that talk next.
Okay, great. Okay, see you.
Thanks, Elaine.
Hello, everyone. My name is Fiona Liu, Technical Services Manager at AOCS. Today, I will be demonstrating how to get access to the two in vitro protein digestibility methods. You can access all AOCS methods from the AOCS homepage at aocs.org. Once you are on the homepage, go to Technical Products tab and click on Methods. This will take you to the AOCS method site at library.aocs.org. Here you can search methods by name, where you can type keywords in the search box, or you can browse methods by method section. The in vitro protein digestibility methods are numbered KA1A 2023 and KA1B 2023. So when you browse by method section, go down the list to section K, pauses. Here you can see the two methods listed. When I click on one method, it shows the scope and the definition of the method, as well as its latest revision status. To purchase the methods, you can add them to cart. This will allow you to purchase the individual methods. Or if you have an AOCS method subscription, these methods are readily available for you to read online or download. You will need to sign in. If you have an individual subscription, you will sign in under the individual user sign-in area. Or if you have a global or university government subscription, you will need to sign in this area. Your email will be recognized by domain. Thank you for your attention. I hope you find this brief demonstration helpful. If you have any questions, please feel free to contact us. You can reach us by clicking on this Contact Us button at the bottom of the page. For technical questions, myself or my colleague Xin Wu can answer your technical questions, or you can contact Julie May for any wording questions. Thank you.
Hey, we're back. We have just a couple minutes here to answer any questions that might come up about how to access these standardized methods. I do have a question about whether the recording will be available for this webinar, and the answer is yes, which would include, you could see some of those slides. I also have a question about what are the AOCS method numbers. Fiona, do you have them handy that you could just reiterate them?
That is KA1A-2023 and KA1B-2023.
Okay. So within a month, anyone who signed up for this webinar will receive an email with the link to the recording, and you've got the numbers, and the slides will show you how to get more access. And I think that's it for this section, and we can move on to our last presentation by Health Canada.
Hello, and thanks for having me. My name is Ashley Wiggins, and I'm going to be providing an overview of protein quality regulations in Canada. I am a senior scientific project coordinator in the Food Nutrition Directorate at Health Canada. So in this role, I work on a variety of food policy and regulatory files, including protein and protein quality. And prior to my work at Health Canada, I managed a tripartite program at the University of Toronto that brought together researchers, food industry, government to address nutrition and food regulatory issues. And during that time, I actually worked with Dr. Jim House at the University of Manitoba on some files related to protein quality. And that's sort of what really sent me on this protein journey that followed me to Health Canada. So it's a real treat to be here speaking alongside others who've worked closely with Jim and to see the advancement of his work on in vitro protein digestibility methods. Okay. So my disclosures, so I'm an advisory member on Protein Industry Canada's Centre for Regulatory Research and Innovation. And I'm also a member of the US Pharmacopoeia Dietary Protein Expert Panel, and I am an employee of the Government of Canada. So, quick overview of what I'll be covering in the next 15 minutes or so. Just starting off with why we regulate protein quality in the Canadian context. Then moving into a very quick overview of sort of key elements of Canadian regulations related to protein quality. And then moving into the methods. So kind of the prior to 2024, what the protein quality method regulations were in Canada. And then since the recent amendments, what the status is now in Canada for protein quality regulations. And then a quick summary. So why regulate protein quality? So we know that not all proteins are created equal, and a diet that doesn't provide enough essential amino acids in a bioavailable manner may cause a variety of health issues. So in Canada, we regulate the protein quality in foods for sort of three key reasons. The first is so that specialty products, so things like infant formula or meal replacements that are used as a sole source of nutrition, provide enough adequate high quality protein. Second is that to help ensure that products that are substitute foods, so these are things like a veggie burger that is being used in place of a beef burger, to help ensure that those products are nutritionally equivalent to the product that's being replaced. And finally, we have regulations in place to help ensure that consumers aren't misled, particularly when it comes to things like protein claims. So we want to make sure that products that are carrying, say, an excellent source of protein claim are providing high quality protein. And having this in place also kind of prevents products from using low quality protein or even non-protein nitrogen sources in their foods to make claims. So a quick snapshot of kind of the key areas in Canadian regulations where protein quality comes into play. So our Food and Drug Regulations, the FDR, requires a minimum protein quality for, as I mentioned, protein claims, both on labels and advertisements. For simulated meat and poultry products, so this is a regulatory category we have in Canada. Basically, it's products that do not contain meat, poultry, or seafood, but have the appearance of a meat or poultry product. So again, think things like a kind of veggie burger that has the appearance of a beef burger. We also have protein quality requirements for infant formula and foods for special dietary use. This is a regulatory category we have in Canada that encompasses several different products, including meal replacements, formulated liquid diets, and nutritional supplements. And just flagging that the infant formula and foods for special dietary use regulations in Canada are currently under review and are set to be modernized in the near future. And finally, we sometimes require a protein quality assessment for novel foods. So novel foods in Canada are products that don't have a history of safe use or have undergone a process which changes it or genetically modified products. So all of these require a pre-market review. So before they can go into market, they have to be undergo a safety review, and that includes looking at the nutritional composition. So sometimes that requires a protein quality assessment. So just digging a little bit a little bit deeper on protein content claims. So in Canada, any representation about protein or amino acids on a label or in an advertisement, that food must meet the conditions for a source of protein claim. So that could be, if there's the word protein in the name of the product, or if there's a statement about, contains 10 grams of protein, then that food has to meet the source of protein claim. Foods can make a source of protein, excellent source of protein, or more protein claim if they meet the criteria that's set out in the table of permitted nutrient content statements and claims. So for a source of protein claim, a food must have a protein rating of at least 20. For an excellent source of protein claim, they must have a protein rating of at least 40. And for a more protein claim, they must have a protein rating of at least 20 and at least 7 grams more protein than the reference food. Now, the protein rating is unique to Canada, and it reflects both the amount of protein and the quality of protein. So now digging into the method. So the Canadian regulations in 1982 incorporated the official method FO1 right into the text of our food and drug regulations. So that made it the only acceptable method to demonstrate compliance with most protein quality requirements. So any change to the official method, if we wanted to change, the methodology of method F01, or if we wanted to add a new method to measure protein quality, that required a full regulatory amendment. Official method F01 requires use of the protein efficiency ratio method to calculate a protein rating. Now, the protein rating is equal to the adjusted PER multiplied by the grams of protein in a reasonable daily intake of the food. And the RDI is a value that's set out in our regulations for a variety of foods. Now, PER is, it remains a valid method. However, there are, as you know, alternative methods available that have some advantages over PER. So in December 2020, Health Canada and the Canadian Food Inspection Agency published an interim policy to immediately accept results from either PER, as we had been using, or PDCAS to show compliance with most protein quality regulations. Flagging that infant formulas were not included in the interim policy and were required to continue using PER due to concerns with the application of PDCAS for kind of accurately reflecting protein quality of infant formulas. This is a space that's, I know, very relevant right now with the National Academies just recently coming out with their report and recommendations on protein quality for infant formulas. So, with that modernization that I mentioned of the infant formula regulations in Canada, we'll be looking at that. So this interim policy used PDCAS to estimate a PER. So manufacturers were advised to multiply the PDCAS by 2.5 to generate an estimated PER, and then that was used to calculate the protein rating. This interim policy was temporary while Health Canada was working to make amendments to the food and drug regulations, which I'm very happy to report happened in December 2024. So as part of a larger regulatory modernization package, amendments were made to the FDR. One thing that happened was we moved method F01, so that PER method, and the associated protein ratings for claims and a variety of foods. We moved those out of the text of the FDR into a new ambulatory incorporated by reference document. And in a moment, I'll explain what that is. So no changes were made to the actual F01 methodology or the protein ratings required. They were just sort of shifted over to this incorporated by reference document. We also added PDCAS as a second method that manufacturers could use to calculate a protein rating of most foods through its inclusion in this new IBR document. Claims on infant foods are currently not permitted to use PDCAS. They're continuing to require the use of the PER method. So now regulated parties can choose which method to use, either PER or PDCAS, to show compliance with most protein quality requirements in Canada. So the incorporated by reference, it's a policy tool we have that allows a document that's not in the text of the regulations to be made part of the regulations. So it has the same legal weight as what is directly in the FDR, but the advantage is that these IBR documents, changes can be made to them administratively. So if we wanted to modify them rather than go through the regular sort of regulatory amendment process, we instead would, do an internal review. Then we would come out with a proposal, which is usually published as a notice of proposal, and that's publicly available, and interested stakeholders can comment on it. And then we collect those comments, analyze it, and then the final changes are published in a notice of modification. And during that process, we also share the proposal with international stakeholders, as well as the World Trade Organization. So it still has that kind of full stakeholder engagement piece, but it's a little bit more nimble. So by moving the methods and the values to this IBR document, it facilitates more responsive and adaptable regulations. So a quick overview of just sort of what things look like now. So either PER or PDCAS can be used to calculate a protein rating. That equation has stayed the same. So the protein rating is equal to either the adjusted PER or now the PDCAS multiplied by the grams of protein in a reasonable daily intake of the food. Now, due to differences in the values of PER and PDCAS, we did establish new protein ratings specific to PDCAS. So I've just given sort of a snapshot of what those look like for the 3 protein claims. So you can see in the middle column, the protein ratings when using PER or method FO1, those haven't changed. They've remained at 20, 40, and 20. However, now with PDCAS on the right-hand column, you can see the protein ratings are 8 for a source of protein, 16 for an excellent source of protein, and 8 for more protein. Now, the methodology for PDCAS we've prescribed and outlined in a second incorporated by reference document. It largely follows the methodology in the FAO WHO expert report from 1991. The amino acid scoring pattern is the 1985 pattern as described in that 1991 report. Protein digestibility can be determined through either rat or pig balance methods or human models, so in vivo. We did look and consider in vitro digestibility methods. However, timing-wise, when we were finalizing our amendments, those methods were still in validation stages. And established amino acid composition and protein digestibility values can be used when available to calculate PDCAS for mixtures. So I just want to emphasize again, having the methodology in this incorporated by reference document means that we can make updates and tweaks to that methodology administratively through that notice of proposal and notice of modification process. Okay, and a quick summary. So there are several regulations in Canada requiring measurement of the protein quality of foods, including to qualify for protein content claims. Most protein quality provisions are based on a minimum protein rating. And since December 2024, the minimum protein rating and the required methods for calculating a protein rating are located in new incorporated by reference documents. Protein rating of most foods can be calculated using either PER or PDCAS methods. And the methodology for PDCAS is prescribed in a separate IBR document and currently requires use of in vivo protein digestibility methods. And just finally emphasizing again that IBR documents are a useful tool we have as they can support more responsive and adaptable regulations that really help kind of better keep pace with science and innovation. So thank you very much. I look forward to questions and more discussion.
Alrighty, so this whole change, congratulations, in December of 2024, of allowing not just PER, but PDCAS is really impactful for all these innovative changes that could be occurring in the food supply at a time when dietary guidance is strongly suggesting that people seek out more diverse sources of protein, getting into many of the plant-based, but really beyond plant-based, right? Because there's many different ways that proteins can be generated as ingredients that can be put in food. So not just plant-based, but that's a really big deal to encourage that type of innovation that's consistent with dietary guidance. So kudos for that. One quick question I had was when you're looking at the claims, you put up the example claims that would trigger needing to do the protein adjust or stating the protein adjusted protein quality or that would limit whether or not you can make the claim is what about a claim that was really simply just characterizing what the source of the protein is? So not saying the number of grams or that it's a good source or anything. It just says made with insert protein, like maybe made with algal protein. Does that trigger, like, is that part of the requirements or are they separate? They're just characterizing the type of protein.
I don't want to kind of step over into compliance and enforcement, which are our colleagues in the Canadian Food Inspection Agency. That's really their space. I can say we do have clearly in our regulations a statement that if there's any if the label contains any mention of protein, it must meet the source of protein claim, other than if you're saying it's low protein. So if you're saying
Okay.
something about the food is low protein, that's carved out. You don't need to obviously meet the source of protein claim requirements, but any mention, if it's on the label saying something about protein, per our regulations, you need to meet that claim requirement.
That's funny because I right away was going, oh, what if someone put not a source of protein?
Yeah. So anything not a source of protein, low protein, for a low protein diet, anything with that, we have an exemption. Yeah.
Okay. All right. That makes sense. So you talked about the fact that the infant formula is still PER based. Did you want to talk about whether there's future plans to revisit that? Or if you did, can you just remind us what they are?
Yes, I would love to. So with those, I think I hopefully made it clear in my presentation. With the changes we had in December of last year, we did not touch the infant formula requirements. So they have remained the same. They are based on an equivalency to casein. So it's not a protein rating, it's an equivalency to casein. And they use PER. That said, we're currently going through a big modernization initiative at Health Canada. So both the regulations for infant formula, infant foods, and those foods for special dietary use, sort of the medical type foods, those regulations are all under review. And it's very timely with the National Academy's recent report coming out. So those protein quality recommendations will certainly be reviewed and considered when we are finalizing our proposal for modernizing the infant formula regulations.
Okay. This is a little bit outside the scope of protein. I'll ask it and you can say whether or not you want to comment on this, but I'm going to ask it just in case. Okay. So the way the US does determination of what would be a serving size on a nutrition facts panel, and hence the value that would be a part of determining whether or not certain values labeled on the nutrition facts panel, as well as the basis for claims, is the RAC, being calculated reference amount commonly consumed into a serving size, whereas in Canada it might be a little different. Has there been talks about harmonizing the basis for labeling amounts between the two?
Um, I can comment on part of it maybe. So maybe just to confirm, yes. So in the US, they use the rack system. In Canada, it kind of depends on what aspect you're labeling. For some things like the protein claims, we use the reasonable daily intake, which we have a table in our regulations that set out what that value is for a variety of foods. We also have a reference amount, and that I'd say is fairly similar to the rack system in the US. So there certainly are differences. I think we are different populations. So those values are meant to be reflective of sort of what the population is eating in a serving. So I think that might explain why there's some of those differences. In terms of harmonizing in the future, of course, it's always beneficial to have regulations as aligned as possible, but I can't comment on if that's in the plans in the future. But maybe just to reiterate again that populations are different in the two countries as well, and regulations reflect that.
Okay, thank you for that. So the IBR, if I remember right, was published before the AOCS published the standardized methods. So what would be the next step to get the validated pH drop or pH death methods in the IBR? I'm not an acronym person. I'm trying hard. The IBR.
No, yes, the IBR.
So that it would be incorporated in there and be allowed in a formal way.
Yeah, so I think in my presentation I hopefully emphasized the advantages of these incorporated by reference documents for our regulations. So it really does allow us to have sort of a tool that we can make updates to a little more efficiently than in the past when we had to do these full regulatory amendments right in the text of the Food and Drug Regulations. So it does open up some doors in terms of ability to be kind of a bit more nimble in keeping up pace with science and innovation. So in terms of the in vitro methods, I mentioned that we did look at them when we were kind of finalizing the amendments, but because they weren't out yet and validated, it just didn't make sense at the time. We do have copies of the two methods, and we are planning to start sort of looking at them, evaluating them on our end in terms of if they're fit for purpose for our regulations. So we're hoping to start that work in the coming months. Once that assessment is done on our end, and if they are kind of fit for purpose for our regulations, we would go through that process that I mentioned where there's a public consultation through notice of proposal. So that would just be a change to that PDCAS methodology, IBR, that I mentioned. So we would go out for a public consultation, interact with international jurisdictions as well. And then if things were, if everyone was supportive, then we could move forward with a notice of modification. So we are looking into it. It's
It's always a process, isn't it?
yes.
With that, we're going to move to the panel discussion. So if Elaine and Fiona, do you want to turn your cameras and sound on? And Adam, I know we don't have a camera on you, but just so people know, Adam is here as well. So any questions you have that you'd like to pose to or across the panel, this is a perfect time to post them. I'm going to start with one kind of big question, which is a question we asked right at the beginning before we even started working on this project, which is if people in North America generally are not deficient in protein as defined by current deficiency standards, which are not optimal health, I'll just point out, but rather at least maintaining minimal growth, or I should say minimal amounts of protein to maintain and sustain growth where growth is relevant. But if we don't have deficiencies, why are we even worried about protein quality? Why don't we just let protein quality go and whatever you put in, label what you put in grams? So provocative question of why this is important to adjust for protein quality and even more specifically, the digestibility part of the equation. And just pointing out for anyone who doesn't recall, the protein quality is two parts, the amino acids. So you're looking at the limiting amino acids and you're looking at the digestibility, okay? So who would like to go first?
I was thinking Ashley might want to comment.
Sure. Yeah, so I mean, protein is a very important nutrient, and as I mentioned in my my presentation, we know that not all proteins are created equal. And on a population level in North America, I think protein, amino acid deficiency, inadequacy are not currently really a concern. We have seen changes in the diet in certainly the last decade or more, kind of moving towards more plant-based proteins, as well as emergence of novel proteins that we maybe don't know quite as much about in terms of their protein digestibility and protein quality. Adam had shown in his presentation a Canadian study a few years ago that was using, I think, dietary intake data from 2015. And, it did show that as you increase the percentage of protein coming from plant sources, there was a reduction in the protein quality of the overall diet. Now, this wasn't looking at health outcomes. It was just sort of looking at calculated protein quality. But I think it does still indicate that it's something we should be kind of considering. And certainly when we're looking at more vulnerable populations, so young children, elderly, that might be particular when they're moving towards, say, a plant-based or novel protein source. So I think it's still relevant, but I'd love to hear Elaine or Adam's ideas on that as well.
Yeah, I'll just pipe in. So I totally agree. And, that protein quality is still something we should be considering, given the fact that new alternative types of proteins may be emerging on the market. But I think also the context of use is important, as I think in the study that Adam and you referenced as well. The poorer protein quality was when people were consuming a lot of cereal grains or bread, and baked goods. And so it does make you think that, well, as novel and alternative proteins do appear on the market, you want to make sure that they're accurately reflecting some level of protein quality, particularly like in one of your kind of guideposts for why you need protein quality is that if there's substitutions for other foods, that they at least meet the nutritional requirements, so that you can't have maybe less than scrupulous manufacturers, marketing like collagen as a sole source nutrition, or, things that, and I think also having protein quality, having the ability in Canada, it's more in your face because you can't have labels saying good source of protein or whatever. I think very few people probably look at the percent daily value on nutrition facts labels. Based on my survey of my neighbors, they don't know what that means. But having people know, it really offers an opportunity for people to say, oh, I see a protein content claim on the product, so this has to have gone through a little bit more rigorous testing and it meets requirements and it's a novel protein. So in that sense, I think it's important, particularly when you're substituting foods that you assume have the same nutritional value and maybe do not. And it allows the food formulators that do have high quality proteins an ability to make those protein claims so that they can inform the consumer that this product is a high quality protein product.
So avoid unintended consequences as the
Right.
food supply is changing, and make sure that we are communicating transparently and honestly about the protein that's in the food, not over promising what's not really going to physiologically be useful. Is that fair wrap on that one? Okay.
Yeah, actually, Barbara, if you don't mind, I was just going to add. So I think something that about this study too that makes it so unique is we haven't looked at protein quality, right, in this assessment, right, in terms of protein intakes, right. So if we wanted to identify even that there's an impact on health or lifestyle or well-being, right, if we're just saying that protein intakes were already adequate, why would we ever study? Right? How do you make a proposal even that there could be risk, right? If previously we're saying we're getting adequate intake. So by using protein quality, now we can say, hey, look, there could be a population at risk, right? And not only how do we assess that risk, but are we even capturing protein quality adequately, right? So there are things like nitrogen conversion factors, right? We might be assuming everything is 6.25, so protein might be higher, right? This makes quality lower for a lot of plant proteins, right? So we might even just be, maybe these estimates are wrong. Maybe the protein intakes from this assessment are fine. And then we're also saying digestibility coefficients are 0.8, right? So we're saying that, we're giving everything a moderate protein digestibility, but when you look at things like breads, they might be higher. They might be closer to 95, right? So these cereals might be, maybe we're saying there is this risk, there isn't this risk. So it opens for more work and proposal in terms of, what if we're getting adequate protein intakes.
Yeah, so take care
Maybe
of the
just
problem before it becomes a problem. Is that what you're kind of getting at?
Sorry, say that again.
So you're kind of suggesting take care of the problem before it becomes a problem, right? Take into account now, knowing the food supply might be changing so that when the food supply is fully changed, we haven't made a new problem.
Certainly, yeah, that's part of it. Yeah.
maybe quickly just picking up on sort of what Adam said and Elaine in that study, the Canadian study. I think like the data we have it's so important. And right now, at least in Canada, the most recent is 2015 dietary intake data. And just think about how diets have changed in terms of protein in the last decade, right? So that study, I think Elaine, you mentioned, yeah, there was a lot of breads and grains that were in that highest, plant protein consumption group, whereas I think there was virtually nobody eating some of these plant veggie burgers, for example, at that time. So I think, getting updated data is also really important to be reflective of, the current landscape.
Good point. So when we think overall of protein quality, we've got the amino acid profile and we've got the digestibility factors. Can someone or more than one of you summarize what impact does the digestibility have versus the amino acid profile? And I ask it because sometimes people look at in vitro studies and say, oh, well, it's just such an estimate, it's such a proxy, and you should be really testing it in people, right? I mean, it's just totally not feasible for any product developer to be running studies in people. That's just off the table. Like even animal studies are pretty much off the table for food companies these days. But like how much of an impact does the digestibility part have? Do we have to have it exactly accurate, or is it a more of a relative accuracy that's most important? Adjust for it, but it doesn't have to be a perfect down to the second decimal adjustment.
Yeah, I want to address, this has been a discussion. I remember reading this book, Protein Quality in Humans, and it's a workshop that was done. It was known as the Airlie Conference in 1980s. And even then, they said in vitro methods would probably be adequate, given the fact that there's so much variability in between humans. And like the some of the summaries were saying, being so precise is probably not warranted given the work that's involved, because you don't know how precise you are because there's so much variability. And I think importantly, if it's not a sole source of nutrition, if you're not talking about a hospitalized person or a trauma, like a burn victim where, high quality protein is needed, or infant formula or a medical food, most people consume all different proteins in the course of a day, even at one meal sitting. So to know the digestibility exactly precisely for each food based on any assay, and then looking at the human, how they normally consume it, it all gets lost in the wash. I think rank ordering, just like they do for all other nutrients, micronutrients, for instance, there are no animal requirements for that, but yet we know that the absorption of calcium, iron, is so influenced by your human physiologic makeup, your dietary habits, your exercise habits. So in that context, but yet those are new micronutrients of concern that we have, but yet there is no animal requirements. There's just a sort of an estimate of the bioavailability of all those things, knowing that it is impacted. So in a fairly affluent society where people consume multiple different protein source foods, I think being so precise is doesn't it's a waste of kind of energy and money. I think for companies to develop protein foods so they can advertise, so that people can go to that product and say, this is a good choice for me, is important. But in the context of health, I think that overall, if people are eating a variety of foods, it's really overkill to measure digestibility, to expect it to be so precise. I think the rank ordering, knowing that this is 75% versus 100%, is more than sufficient.
Okay, so fit to purpose, right? So,
Right.
you know, the amino acid, limiting amino acids is really important and a big part of the protein quality. Digestibility is a small part of it, but an important part. And fit to purpose would be an in vitro assay that's ethically cost efficient and feasible, makes good sense for screening and making smart choices.
And that people will actually do it, because right now they're not. A lot of people are choosing not to even
Can't,
do it at
right?
all.
Most
So
companies have policies against animal testing, so they
yeah.
can't even do it. Anyone else want to comment on this before we?
Yeah.
Oh, sorry, Adam, go ahead.
Okay, sure. I feel like, there's like this progressive science perspective of, should we change nitrogen conversion factors? Why do we even use nitrogen conversion factors, right? When we measure amino acids, right? We know proteins are made up of amino acids. Why don't we just say, on labels, we know what is a protein, what's its total amino acid nitrogen content, let's say. So there's this slow moving goalpost of the science, and I feel like protein quality assessment is really under the microscope, like as Elaine is saying, right? We take in a lot of these other factors before we report something. So maybe just amino acids in themselves should be like the baseline, and then you go from there. Maybe digestibility is this secondary objective, and then even in a sense, if you look at things like reactive lysine or availability of lysine, if that was the measurement, that kind of captures digestibility in a sense, because it's going to reduce the protein's ability to be broken down, right? And it forms aggregates and things like this. So if you were just measuring reactive lysine, right, that seems to be the risk in infant formula and spray drying and heat treatments and Maillard reactions and cereals and things like this, right? So it doesn't even need digestibility; it's just an amino acid analysis. But that might be asking for more too, right? In terms of what labs need to deliver on and food labs.
Ashley, did you have something to add?
Just to kind of pick up one of the points Elaine was making, which I agree with, and it is a tricky thing as a regulator, is we know that, outside of maybe certain medical populations, people are eating a variety of protein foods in the diet, and there's complementary, kind of make up for lower protein quality of one food with another. So that's where, in dietary guidance, something like the Canada Food Guide, and here we have in Canada, that's where you can really sort of describe some of that, eat these types of foods. But when it comes down to labeling of an individual food, it's very difficult to try and reflect that whole diet approach, because we are having to kind of look at it in a silo, even though we know that it's being eaten with other foods. But that's sort of one of the balancing act, I guess, and where, I try and look at things together in terms of our dietary guidance that we have in nutrition policy with the regulations, which are much more single food focused.
Yeah. I think there's a question here too about how often do consumers look at the protein information in foods, and specifically, do they even know about protein quality or how to look at it? So it's kind of another whole question that we're not addressing today, but I just want to put out there and say that that's another whole point, is how to keep consumers tracking with selecting quality foods when they have no idea um, what the impact of a particular ingredient choice or processing method is, right? So protein quality tries to get at that, but it's kind of behind the scenes, I think, for most consumers. So parting thoughts, we have last 3 minutes of the panel. If there's any last advice you want to give to a product developer, maybe who's getting ready to develop a new product or improve a product they have, or anything else that you'd prefer to say, and we'll just start with Ashley, go to Elaine, go to Fiona, and go to Adam. If we can do it in that order, it'd be great. Thank you.
I would say just from Health Canada's perspective, if you have questions, if you're developing a new product, especially if it's a novel food, engage with us, we say early and often, to avoid sort of heartache down the road. We are always open to chat if you have questions, or if you have a new food that you're developing and you want to see how it would fit in with the Canadian framework. Please reach out. It's better to address the questions early than when you're ready to go to market.
And as far as I'm concerned, I'm excited that there's this standardized. The AOCS helped us develop the standardized in vitro methods, and so it provides food formulators, ingredient manufacturers with a great tool. And now there's less of an excuse not to use it, to actually help develop your products. And at certain points in your process and development, you're going to want to use these. And what I think it does is it gives you more scientific credibility that you're doing the work to make the claims based on protein quality. And it prevents litigation that you didn't measure it correctly, at least as you develop it. So I think it provides more scientific credibility. It ensures a higher quality product and will eliminate any processing or formulation things that are kind of dead ends that are not good for your particular protein food.
I will comment on the use of AOCS methods. If you ever encounter any technical issues, feel free to contact me. We can always reach out to the method proposers. We also have groups of experts in the industry, as well as a methods editor-in-chiefs to answer your technical questions and help you utilize the AOCS method.
I think Elaine captured how the methods could be used accurately, and I'm not sure I have much more to add to that. But if anyone has any questions or research ideas where they want some input, I'm happy to answer those questions. These recordings are up, are coming up, right? So you'll see my email there if you need to contact me. Thank you.
Perfect. Thank you. We can go to the last slide. In going to the last slide, I just want to remind everyone that what we've talked about here is a tool that is standardized for use right now by product developers, but anytime you're getting to final labeling requirements of calculating your protein levels or claims or percent of recommended daily values, just keep in mind that is a separate discussion for which every country has very specific rules, and you need regulatory expertise to figure out what you need to do for that final product as it's going to be labeled. So with that, I would say thank you to all of our speakers today. And also comment that if you have any interest in being added, for example, to IAFNS webinars or events list, the email that you would send that to is currently posted on the slide. Just let us know, and we're happy to add you to our distribution list. And with that, have a good day, everyone, and thank you for being with us.
Thank you.
Thank you.
Thank you.